Good morning or good evening. It's me again, Jean-Louis Van Bella. I'm a bit of an amateur physicist. Um, I've done a few recordings, a few videos here, and so this I think might be my last one actually, where sort of I bring a few things together in a more of philosophical approach, because my other videos, if you look at them, you'll see it's a lot of formulas. The theme though was interesting. The theme is really to sort of look at how we can, possibly imagine some kind of realist interpretation of quantum physics, rather than, all the weird stuff you have around. Basically, what we say like, well, we have this wave function describing something, but then, we need to sort of, take its absolute value and then square that absolute value, and then we get some probability that a probability that an observable is equal to some value. So I think we have a realist interpretation, and it's kind of close. Um, and that's sort of where I want to really go into. I've published a lot of papers. You can see it there on the list on the website of basically Phil Gibbs, who's like an independent mathematician and physicist, sort of, who acknowledges that a lot of the creativity is going out, outside of academics, and so who offers like, publishing or publishing site for authors like me. And then I have my two blogs there, and actually, the paper I'm gonna discuss now has been published on the blogs, and it's sort of still like being on hold on the other side, the vixra.org site. So, but let's go for it. It's sort of like really, I said. I think all the papers, I've got 24 papers now, and sort of like years and years and years of articles and blogs and thinking, saying that there is actually something like, a realist interpretation of quantum mechanics, something we can imagine and in exactly the way we want to imagine it, something in, 3D space and in time. And, but here we're really sort of going to look at, if our interpretation is right, which we think it is, of course, because it's our interpretation, then where is mainstream quantum mechanics? Where do they go wrong? Where exactly? What sort of the fallacies or sort of the logical inconsistencies in that model? They cannot be huge because the theory produces the right results and the right predictions and explains everything. We just don't know why these particular rules of, taking the absolute square of a wave function and this and that, and all these weird, statistics for bosons and fermions are there. So this sort of delves into that and sort of makes the case that, we can simplify an awful lot. Okay, I'm sorry for this slide, but I didn't want to put too much time in this video. I didn't prepare it very well. I've got a day job, and that's where I just thought, okay, my first slide, I'm just going to put the text there basically and explain what this video is about. The video is about, modern quantum theory and how we should, interpret it, and if there's sort of a viable alternative to that interpretation. We know the standard interpretation is just like, quantum theory is what it is. So we have, these guys there that I mentioned, Dyson and Schwinger and Feynman and Tomonaga, and a whole second generation of physicists who, basically soldiered on. There were some, with this quantum mechanics is weird, and but they soldiered on and developed a whole theory of, perturbation theory and, propagators. How does an electron go from here to there? It's basically, if you want to sum it all up, it's sort of like, quantum field theory, it's called. It's a theory about interactions, and that's sort of really the problem that really bothered me and that I sort of noticed. It's sort of, modern quantum electrodynamics talks about explaining the behavior of electrons and photons and their interactions between electrons and between photons and between electrons and photons, and then probably some other particles, protons and neutrons. But basically quantum electrodynamics is pretty much about electrons and photons. We think about electric charge and electromagnetic fields, and so yeah, we want to sort of reconcile the wave and particle behavior of what we think electrons and photons are, and that's exactly where the problem is, because that theory, modern quantum theory, actually, you can look, but it doesn't have a good description of what electrons and photons actually are, and so basically all of the weirdness of quantum mechanics, and you know what the weirdness is, it's sort of these interference effects and between what we think would be particles, an electron, you send it through slits, and then you see sort of the distribution of how that where the electrons really hit the detector. So there's interference there, so it's got like a wave character, but because we actually sort of don't have a good description of what electrons and photons are, I think this whole second generation of quantum physicists have sort of developed a theory which really, yeah, all of the weirdness is in the fields. And that's really, just as an example, you've heard about the path integral formulation of quantum mechanics. That's linked to these, propagators, where we say, like, we have an electron or we have a photon, and, it goes from A to B, and sort of what is the probability to get from A to B, and what is the probability, if it's not getting to B, that it will end up in C or another spot. And so the path integral formulation basically, says that, oh, well, you need to go through the motions and sort of, try to calculate the amplitude for that particle traveling along really an infinite number of possible space-time trajectories between A and B. And that's something what I put here, whatever an electron or a photon might be, can we really like believe that it travels along an infinite number of possible space-time trajectories all over space or all over time? I don't think we can, and that's sort of what continues to trigger that search for what is called a realist interpretation of quantum mechanics. And then there's a lot of other weird stuff. You've heard about the anomalous magnetic moment. Yeah, the magnetic moment of an electron, we know it's a property, it's spin. Fermions have spin, bosons have spin, but fermions for sure, electrons, even neutrons, they're neutral, but they have spin. So it's like some kind of electric current going around and creating some magnetic moment, and it's slightly off actually of the value that you would expect if an electron would really be like a point-like charge. If it's a point-like charge, the value would be like 2 or 1, depending on whether you look at an electron as a spin-only electron in free space, or whether that electron is basically in some orbit around the nucleus, or in one of these experiments, basically an electron is being is orbiting around some center in what is called a penning trap. You have an electromagnetic field that keeps the electron in place, but it keeps it in place, but it's it's spinning around. So you have some theoretical value for the magnetic moment then, and but what is measured is that it's slightly off, and so yeah, you have that tennis match, as they call it, between experiment that sort of establishes that value that is slightly off 1 or slightly off 2, and the theory is based on quantum field theory, and works with these an electron interacting with itself, and it can do so in a pretty straightforward way. We have sort of a one loop vortex or a one loop interaction, but you can also have 2 loop interactions when all kinds of funny things happen, 3 loops, 4 loops, etc. So the it really becomes very, very, very complex, and you know, for the moment, actually, the theoretical calculations, as I put it there, are sort of, you know, based on for loop interactions, and you know, we have all the possible um, paths over time and space, and now we've, well, it sort of amounts to like 891 for loop Feynman diagrams that you need to calculate, and you know, these calculations involve integrals, and so there's something like, you know, this can't be right. We don't have a decent electron model, and so yeah, um, we don't have a form factor or something. Do we picture the electron as a disk or a sphere or something else? You know, we really need like a good electron model to explain all that kind of stuff, and that's what's lacking in modern quantum theory, in my not so humble opinion, I must admit. Am I arrogant? Am I an arrogant guy? Yes, probably I am. You know, I'm 50 years old. This is not my day job, and yeah, I'm looking at this stuff and I'm feeling like, yeah, it must be something that explains it. And I think I'm in good company, and that's sort of what kept me going. It's sort of like, Einstein was very critical about you know, classical or the mainstream interpretation of quantum mechanics. But it's not only him. You know, Schrödinger, Dirac, Pauli, Heisenberg, all sort of the whole first generation of quantum physicists. And you know, even I talked about the second generation of physicists, Dyson, Schwinger, Feynman, but the third generation is like people like Bell, you know, who established his no-go theorem, which basically said, you know, well, this is not a great interpretation, but you know, there's nothing else around. And there can't be anything else around. But he himself said, like, you know, I hope one day somebody will disprove my theorem, Bell's theorem, no-go theorem, and he also acknowledged that, like, you know, the math of that theorem is right. There must be something wrong in the assumptions, and so that's where I think we're in good company, and we should sort of pursue this venture of finding a common sense interpretation of quantum mechanics. I just would like to quote Dirac here, who sort of, you know, it's kind of amazing. He sort of helped to, you know, he laid the foundations actually of perturbation and renormalization theory. So he really bridged the first and second generation of quantum physicists, and sort of, I mean, a lot of what is around is still like, you know, basically that's Dirac. I've got his principles of quantum mechanics here on my desk, and you know, basically that's a book that's written, what is it now in his edition, 1927 or something, but you know, it's pretty much what whatever book of on quantum mechanics you'll read tells you nowadays. But so he sort of you know, while creating this theory, and sort of, you know, just, you know, a few years before his death, he said, I'm not happy about this theory, you know, perturbation renormalization theory, and let me read it. I'm very dissatisfied. It's a good theory because, you know, it gives the right predictions, but it involves neglecting infinities. And it's just not sensible math. Sensible mathematics involve neglecting a quantity. When it's small, you don't neglect it just because it's infinitely great and you don't want it. So, I mean, Dirac, like many other great physicists and scientists, it's kind of sad the way he died, in terms of, you know, being, you know, looking for the truth and looking for a model and looking for a theory, and but yeah, these guys sort of got marginalized, and yeah, there were people like, yeah, Dyson, Schwinger, Feynman, who sort of, you know, said, well, just do the math, just calculate, and if the results are if the results agree with experiment, that's all what you want, right? Well, maybe not. So I said, I've sort of you should go to my papers and the site and whatever, to sort of see that alternative interpretation of quantum mechanics that I'm offering, in terms of you know, there's actually this, it's called the Zitterbewegung hypothesis. So Schrödinger and Dirac, they discovered there's like a very trivial solution to Dirac's equation for an electron in free space, which basically says that, you know, the electron is like it is a naked charge without rest mass, and so that means that it has to move around at the speed of light always. And it does so in a kind of circular motion at a very, 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 very tiny scale and at a very, 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 very high frequency, which, as I show in my other papers, is really, given by the Planck-Einstein relation and the mass-energy equivalence relation of Einstein. It's basically, it's really Wheeler's idea of mass without mass. An electron is kind of this hybrid thing where we have a naked charge. So that's kind of an object that has, it has only charge, electric charge. It has no mechanical mass, and so as soon as you apply a force to it, an electromagnetic force, magnetic or electric, then it's going to accelerate to infinity. I mean, to infinity, to the speed of light, because that's the maximum speed anything can achieve in the universe. And so, yeah, it's going to sort of wiggle around, and so that's the Zitterbewegung interpretation. And sort of based on that, you have a realist interpretation of quantum mechanics, which I'll explain. But so the mainstream quantum mechanics, the Copenhagen interpretation, sort of missed that. And here I just want to show a few slides where that's really the basis of sort of the mainstream interpretation, and of sort of in terms of amplitudes and how bosons are supposed to interact, and how fermions are supposed to interact, yeah. So the analysis is very simplistic in the sense that this is the diagram really. We have a particle A on the left hand side, and we have a particle B on the right hand side, and they're gonna collide elastically. And there's two possibilities really, that A ends up in detector 1. So A goes from left to right on the left hand side of the slide, and it ends up in detector 1, and B then accordingly bounces south and goes into detector 2. And then the other way around is sort of, when you look at these angles, is that A goes into 2 and B goes into 1. And he basically says, well, the assumption is that A and B are identical. But what does it mean, an identical particle? For Feynman and generally, a particle here in this picture is some kind of, what is it? It's an identical particle, but what properties does it have? It probably has some mass, right? Mass is just a scalar number. It weighs 3 kg or 4 kg. That doesn't have any, spin. There's no spin in this picture. That's basically the issue. These are spin zero particles. These are point-like things that collide. And so that's a very, very classical analysis, I would say, where basically we're sort of, analyzing stuff from this, in terms of Lagrangians and Hamiltonians, where basically, we think of stuff as being point-like, having no dimension, and then sort of bounce around and having some momentum and having some mass, but nothing more than that. And so that's basically where the big mistake is I think in sort of the classical, or let's say the mainstream, the Copenhagen interpretation of quantum physics, is that we sort of we know real life, all particles, they have spin. A proton, a neutron, an electron, a photon, it has a spin up or down, and that's sort of what really is an intrinsic property of that thing. But at the same time, when we build up our theoretical framework, we sort of forget about that, and that's sort of where things get very ambiguous. And then for me, it's the sorry to say, the bullshit in, bullshit out principle. If you sort of don't have a very solid and unambiguous description of sort of the states where you start with and then where you end up with, and how can you expect to have sort of a theory that is like consistent and understandable? So let me explain. So Feynman's logic is basically, so he says that there's a probability, well, actually there's an amplitude, because you have these quantum mechanical rules, right? We think about amplitudes rather than probabilities. Well, we think about probabilities, but probabilities, are the absolute square of an amplitude, and that's where also these mathematics are a bit funny. where they don't explain those rules. You know, they just say like, you have an amplitude, we don't know what it is, but you need to take the absolute square and then you get a probability. And that's sort of where I think like, well, have you thought about mass densities or energy densities? If an amplitude is something real, then probably, you know that the energy in an oscillation will be, proportional to the square of the amplitude and square of the frequency. And this sort of, try to think of what explain. But in case Feynman doesn't do that, he just says, well, there's an amplitude, right? Not a probability, an amplitude. This weird quantum mechanical concept, and there's an amplitude for A going into 1 and for A going into 2. And then because of that situation there, if A goes into 1, then B goes into 2. And if A goes into 2, then B goes into 1. And so then we need to sum the amplitudes before we square. We take that absolute square. And then yeah, that amplitude, of course, is going to be a function of the angle of collision there. Well, not the angle of collision, because the angle of collision is just like it's a head-on collision, but the angle of A and B bouncing in the detector, the angle between the A and B axis and then the detector, the axis between the detectors. So the first amplitude is going to be a function of that delta, and then the second one, you can look it up actually. It's sort of, this is Feynman, volume 3, his lectures on quantum mechanics, chapter 4, identical particles, and then he'll calculate that to you, where basically he says, okay, the second amplitude is going to be a function of the of p minus delta, and actually it's not going to be a function of p minus delta, but we have that phase factor there, because exactly, we need to take the absolute square to get the probabilities again, and so the we have a phase factor E, the Euler's number times the imaginary, so the exponent there is the imaginary number times delta, phase factor, another delta, small delta. So so he's thinking about that phase factor, because as he says there, the phase factor is very important. What could it be? And then he sort of goes into this weird reasoning where he says, let's exchange the role of the two particles. They're identical, but let's put A on the right hand side and let's put B on the left hand side, and then because they're identical, we should get the same amplitudes, the same probabilities, and so yeah, it's a really funny reasoning where we exchange them, and then we put A where B should be, and we put B where A should be, and then we exchange them again, so we should get the same factor again. So it basically means that phase factor must be, its square must be equal to 1, because if you exchange, you will multiply by the phase factor, and then you will multiply by the phase factor again. So basically you take the square of that phase factor, and must be 1. And so he basically says then, okay, fine, we have a positive square root of 1 and we have a negative square root of 1, and so that e to the power I delta is going to be plus 1 or minus 1. So and then he concludes basically, I said this is a text, I'm copying it here. It's sort of like I'm telling a lot of stuff that is not there, but the reasoning is really then, yeah, either the exchanged case contributes with the same sign, if e to the power I delta s is plus 1, or it contributes with the opposite sign, minus 1. And he says both cases exist in nature, and one is just a collision between fermions, and the other one is a collision between bosons. And if it's plus 1, then it's Bose particles and bosons, and the other ones are Fermi particles. And so then basically, boom, that's the grand conclusion. If we have Bose particles, bosons colliding, then the amplitude of that event is going to be given by positive interference. We're going to have the amplitude, of A going directly to 1 and then B directly going to 2, plus the amplitude of when A goes to 2 and B goes to 1. But it's kind of funny, really, because first bosons, he's writing this in 1963. What bosons were around? photons, basically. Photons, they don't collide. They just don't. There's photon-photon interactions is something that, it happens, huh? Photons interact with photons, and there's sort of these, well, can we call it collisions? Sort of recently, there's been a lot of research on photon-photon interactions, on collisions between photons, if you want to call it that way. But at that time, 1963, he was writing about, electrons, and I mean, his mental picture at least was about that, about protons and neutrons and, helium nuclei or hydrogen nuclei, which is a proton. So, especially because, what is a particle, right? Particle, an electron, a neutron, it has some mass, and then what else does it have? It has this property spin, they're spin 1/2 particles. We know that. While a photon, we know there's no like charge involved. Photon is not going to be attracted by another photon because it has the same charge. So photons don't have any charge. And their spin, they do have spin, but the spin is some integral multiple of h, or h bar if you talk about angular momentum. So it's kind of a really weird reasoning where basically, he talks about theoretical identical particles, saying that, well, there might be bosons, or well, there might be fermions, but you don't have a clue what he's talking about here, really. It's just like it's this sort of theoretical spin zero particle. That's it, basically. A and B are theoretical particles with no spin, and then you wonder, like, they're really theoretical particles in the sense that they're non-existent. They don't sort of correspond to anything that we know. We know how electrons behave with protons, neutrons. We do experiments with them, and what comes out of these experiments is that they have spin. We polarize beams, we depolarize them. We have we make them collide, and then we see what happens with sort of when they hit each other hard enough. We got a sort of a mess, and then things come together. But bosons colliding. I mean, 1963, no photons were colliding. I mean, there weren't any of these experiments. The boson photon-photon interactions is sort of a really high, super high energy physics that wasn't available at that time, and that's really where this logic comes across as being kind of weird and quaint. So again, here, sort of, I mean, the first question that comes to me, also to mind, is like, okay, fine. I know Richard Feynman didn't like philosophers, and he didn't like these kind of blunt questions. But if you're describing reality, which I would hope physicists are trying to do, is a rule like that where say, well, we have an amplitude. We don't exactly know what an amplitude is, but it's some kind of theoretical physical concept and this and that, and we know that an amplitude has to be added with the positive signs when we're talking bosons, and with the negative signs if it's fermions, to sort of give us the outcome we want. I mean, my first question is, what the hell? How would nature know whether we should add these kind of amplitudes, or that theoretical concept which we have never really defined in the first place? How do we know? How would nature know? Because we're talking about things that happen in reality, and again, that's what I read here. It's really obvious. Feynman does not really present a real particle here. These A and B particles are theoretical zero spin particles, and so we're somehow supposed to think about them in a very abstract and imaginative way, without thinking they have spin, which they have, and sort of which determines their behavior in whatever experiment we do with them, in a Stein-Gerlach apparatus, or an interference apparatus, or whatever. And so we're supposed to do some thinking about how these things interact without actually, these particles A and B are totally abstract, and so then sometime later in the theoretical development, Feynman will bring that spin property back in. I show that in the paper, but he really brings it in through the back door, a few chapters later, or whatever. So and again, it's really like, we know particles A and B, because that's what he's trying to show in this chapter, is either it's a fermion, right, or else it's a boson. And so we develop a model or some theory about bosons and fermions based on, well, on what? Identical particles are, what other property do they have besides mass? Mass is a scalar number, right? We know, like, I mean, yeah, in the Higgs sector, we sort of think of mass really as a scalar field. So actually, don't think of mass really as a property of a particle. It's just it's a number you attach with a certain position in space-time, and then, I mean, the whole realist interpretation we developed is also based on that. You know, the mass is just some kind of you know, equivalent mass of energy, and the energy is in an oscillation of some of a charge, basically, for fermions. And so you really think, like, what other property do they have besides their spin? So if you abstract away from spin, you know, what are you left with? So and then the other question is really like, how can we possibly think this diagram could depict a boson? I mean, I said photons, they don't enter into elastic collisions. Photon interactions indeed are relatively new. You know, it's sort of stuff you do with very, 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 very high energy photons, really in sort of the gamma rays. And so you really wonder, what did Feynman had in mind here? I mean, for all practical purposes, he was thinking in terms of electrons, protons, neutrons, and other simple particles. And so he should sort of you know, talk about their spin, which is you know, 1.5 times h bar, the reduced Planck constant. So this is sort of like a generalization where it looks weird, it sounds weird, it feels weird, and basically it just is weird. So that's where, you know, if you look at sort of an elastic collision experiment, and you accept that sort of like, yeah, when we talk something real, it will have spin. You know, that's the thing in sort of the quantum physicists, you know, Dirac, Schrödinger, and whatever, when theory was being developed, they didn't think too much about a strange property of spin. It was sort of an auxiliary thing, and so, oh, we'll plug it in back later. You know, we have a Schrödinger's equation for an electron orbital or electron orbitals, and then we'll sort of, you know, we add a quantum number because we know that, you know, we can have spin up and spin down, and if we have two electrons, one with spin up and one with spin down in an electron orbital, it's going to sort of, you know, reduce energy and as of the system as a whole, and then that's where we're. But the point is, you know, particles will have spin. And that's where, you know, if you think of an experiment like this, you should, you know, the spin of A, you know, and especially in these kind of experiments, you will use polarized beams. You know, you will align you will make sure that the velocity and the momentum of these particles is just like, you know, just right to hit the other beam. And so, you know, you will do all kinds of manipulations with in these collision experiments to make sure that your beam of A particles and your beam of B particles, you know, collides, and at a very specific point in space and in time, and so you will know, you will prep those beams, and these are not going to be unpolarized beams. You're gonna, you know, you're gonna have electrons with spin up, you know, that come out of your Stein-Gerlach apparatus, or your you know, whatever apparatus they're coming out of. The spin is going to be up or it's going to be down, and conversely, for the other beam that is coming in, you will know that the spin is up or down. You will control that experiment, and if you don't control it, I mean, okay, fine, then you'll have different results, but then you know that you haven't been controlling, you know, the initial conditions, and then you know, to find out what happens exactly and correlate these results to what happens with polarized beams, you know, it's just like, you see what I'm saying? Like, you know, you will what you have in terms of when you're analyzing the initial and final states of an experiment like that, you will have like 8 um, um, theoretical situations, and then you can talk about, you know, how can we distinguish them, and that's the problem really. Like, you know, if the spin of A is up and the spin of B is up, then whatever happens, if the collision, I mean that's the principle of conservation of angular momentum or conservation of energy even. It's sort of like the collision is not going to change the spin of those two particles. I mean, we could build in that assumption as well, but for the moment, let's not build it in. But we will know that in detector 1 and detector 2, we'll have a spin-up particle. We don't know which one is A and which one is B. Depends. A might have gone up and B might have gone into detector 2. But that's the thing. And then spin of A is down when it leaves the apparatus, and the spin of B is up. Then we have these. Now we have two situations which we can actually distinguish. Detector 1, if A goes to detector 2, then detector 2 will detect a spin down particle, and B will end up in detector 1 and will be spin up. Or conversely, the other way around is detector 1 will have the spin down particle, will have A, and D2 will have the B particle. And so you see there, basically what I'm putting in that table is there that we have like 4 kind of combinations based on the initial state of particle A and particle B, and then we have 1, 2, 3, 4, 5, I mean 8 possibilities that we have there, but to distinguish them, like, we only have 4. I mean, in the upper left corner there, we say detector 1 detects a spin-up particle. Yeah, but that spin-up particle might be A or it might be B. That's where we can't distinguish the two particles, but we do know it's gonna have the spin of the particle that came in, that was sent out of our apparatus. And so that's kind of the logic where you would want to have really a description of sort of these initial states and final states in terms of unambiguous descriptions, not sort of like, oh, we have a wave function here and it is some kind of theoretical spin zero particle. No, our wave function, which I'm putting here, it's that complex exponential. The sign of the imaginary unit there is basically either left hand or right-handed polarization, and that's what you have at the bottom there. So spin, the direction of travel, a particle can travel in a positive x direction, and it can travel in a negative x direction, and it can have its spin up, or it can have its spin down. Look at that table there, and we know that the spin angular momentum has a value that's equal to h bar divided by 2. That's what fermions, all fermions have that. I mean, fermions spin 1-2 particles. I mean, elementary fermions. And so that's the crazy thing about mainstream quantum mechanics, that for some reason, the professors decided to sort of say like, well, it's true, we can sort of do. We can make some kind of choice here, it's not really relevant. We have a particle traveling in the positive x direction or in the positive y direction, and then we have two possibilities. We can choose to have a wave function that is with a positive imaginary unit or the negative one, and we just choose one out of the two, and then all the physicists take the same convention. But you end up in this mess where you're not describing your initial states properly, and everything is tied to everything here. Where if you do sort of think like there is a physical interpretation of the wave function, and you're gonna sort of say like the sign of our imaginary unit models basically positive spin or negative spin, spin up or spin down, then it sort of trickles down to whatever you do, and that's really where Feynman, I mean, and the early, I mean, even the first generation of quantum physicists, they went wrong in this thing where they basically didn't think about that basic epistemological principle, Occam's razor, I call it. They say like, if you want to develop a good theory, you should make sure that your mathematical descriptions, I mean, the thing you want to describe and the way how you describe it, that they're like linked up, that the concepts you are using, the mathematical concepts, the mathematical shapes, these wave functions and whatever, that they sort of, you know, want that's not ambiguous. And that's really it, because I mean, this is gonna get like super technical, and I don't want it to be super technical. I sort of just wanted to give you a bit of a feel where sort of realist interpretations of quantum mechanics and the mainstream interpretation of quantum mechanics bifurcate. Is that a correct English word? So we already sort of separate. And it's really that deep philosophical epistemological principle which you know, guys like Richard Feynman look down upon. I mean, I made a lot of negative remarks about philosophers, but if you start off with ambiguous descriptions of stuff, if you sort of don't know what you're describing, then you know you're in this mess, and that's where I think sort of what I try to show in all my papers is that if you get that right, you can explain a lot of stuff in really, you know, very common sense. Classical physics, relativistically correct and everything, you know, no issues with that. Maxwell's equations, you know, just geometry. I mean, complicated geometry, because you know we have these weird orbits and, you know, classical couplings between, you know, spin only angular momentum and orbital angular momentum, and so it's very complicated. Classical electromagnetics is not an easy thing. And then when you inject what you inject with quantum mechanics is sort of that discreteness of stuff, where you basically say, well, an electron is going to pack, you know, a discrete amount of energy, and that discrete amount of energy is going to be, you know, a function of what's dictated by the Planck-Einstein relation, where, you know, energy, we're talking some oscillations. So in one cycle of that oscillation, we have you know, potential energy that changes, and we have kinetic energy, and so but the sum of that potential and kinetic energy is going to be the energy of the particle, and it's going to be an energy that is related to a cycle, a fundamental cycle of our particle, and the cycle is governed by Planck's quantum of action, because a cycle packs, you know, a certain amount of force over a certain distance over a certain amount of time. And so then basically, you know, things are still are complicated, but they're not that complicated. And yeah, that's what I wanted to talk about, and I hope you're gonna explore yourself further. And I said I could talk for hours and hours, and but I haven't prepared for that, and I know I've been talking too long already. I just want to give you really a feeling that you know, regardless of what all these guys tell you, and you know, I've done the MIT ZDX course, and you know, my son is studying for engineering, and he's got a course in quantum mechanics, and I'm going like, what the hell? Basically, it's just like repeating stuff, you know, models reproducing things that they don't understand. And the academics that teach these subjects, they don't understand either, and it's really sad, because they're sort of stuck in a straitjacket where, well, you know, the mainstream interpretation of quantum mechanics has led to a number of weird theories and weird explanations, which are correct. They sort of, you know, give an explanation somehow of some kind of experimental result, but honestly, it can be simplified. And so I hope you will have fun with that. And I'm sorry I'm rambling a bit. So yeah, have a look at this. These publications have my email also, so if you want to give some feedback, even if it's just to shout like, you know, you're really crazy, which probably I am, then yeah, give me that feedback, and I'll try to reply to you, and let's see where we get. I mean, it's really we're all looking for some kind of explanation of what you know, what world we are living in, right? And so that happens at different levels, you know, politics and society and our family and then, you know, values and this and that. It's sort of like, for me, this is like, I mean, physics is the king of science, right? Math is often defined as the queen of science. So math is in the service of the king of science, of physics. But yeah, it's sort of sad that after, you know, 100 years, more than 100 years after, you know, Paul Dirac, and let me take his book here. I think it is from 1927. I'll just quickly check his first edition. 1930. Okay, any case, from 1930, so it's almost 100 years now since Dirac published his Principles of Quantum Mechanics, which is still used as theory, and we're in this weird world where we use math in a way we don't quite understand. We don't feel it sort of like makes sense in terms of you know, a common sense and understanding in terms of three-dimensional space and time, which goes in one direction only. Okay, I'll shut up, and good luck with it, and let me know if you think this is interesting, because that would be encouraging, because sometimes I wonder what I'm doing. And yeah, take care. Bye.